A VLS designer plans to pipeline a data path using D-type flip-flops with a tclk-to-Q of 44 picoseconds. Tsetup is 23 picoseconds, and thold is equal to 20 picoseconds. Now we have a clock, and it's used with 16 logic gates between flip-flops, and each has gate delay of 34 seconds. But problems are going to look very different. If you have something similar or a little bit different, you can kind of rearrange the formula that we're going to use to solve for this. But for this one specifically, we're going to want to pay attention to all the variables that are given. Specifically, we are going to tie the 16 logic gates with our gate delay, right? Because we have 16 logic gates between our flip-flops, and each gate delay is 34 picoseconds. So each one has 34 picoseconds, and we have 16. So that's how we look at that. We're specifically asked what's the maximum clock skew that can be tolerated. So that's going to be our step one. We're going to calculate the total gate delay. And that's just going to be whatever value the logic gates are times the gate delay. So ours here is 16 times 34, and this is 34 picoseconds. So this is going to give us approximately 5.44, and then this is 10 to the negative 10. So this is our entire gate delay. Now the next thing we want to calculate for is the clock skew. And for the clock skew, we can actually look in the notes that are in the description below the like button. So we can take this, go back in our notes, and from here we can just plug things in. Now T is going to be the total time. We're not given time here, we are given 573 megahertz. This is frequency. So to go from frequency to time, we just need to be 1 over our frequency. So 1 over 573, and then mega is just e to the power of 6. Now we want to find the clock skew, right? That's like our overall answer. So we're just going to move everything over to the other side. So minus TFF, and then minus TD, minus TSU. This has to be greater than our TS, and that's going to be the answer. So for our TFF, this is simply going to be the D-type flip-flops, right? That's the flip-flop delay. So for this one, it's just going to be 44. So we have 44 picoseconds, and remember a pico is just equal to 10 to the negative 12. So we have 44 picoseconds there. We have our TD, and the TD is just going to be the gate delay, and we've solved this. So the gate delay, we found it in step 1. So gate delay is just going to be 5.44 and then e to the negative 10. And then lastly, we have our TSU, which is the T setup time. And so for our T setup time, it's just going to be for this problem, it's 23 picoseconds. And so that means that our TS has to be less than, if we go to here, a 1.134, and then we have e to the negative 9 or 10 to the negative 9. We want our answer in picoseconds, so we're going to multiply this by 1 pico, and then it's over 10 to the negative 12. And then if we do this, we are going to get that our answer is, and for this problem, your variables might be different, 1134.2 approximately. So that is how we would calculate for our clock skew and solve for this problem.